Okay. Ladies and gentlemen, my name is Tomasz Praczyk, and together with Piotr, Szymak, we are authors of the paper and the presentation entitled, you can see, Neural Swarm Control Algorithm for Underwater Vehicles. This presentation, how can I skip to the next slide? Okay. This presentation shows you first results in CBVS2 project. CBVS2 project is EDA, so European Defense Agency project. The objectives of the project you can see in the slide, generally to develop underwater swarm technology. In our project, we assume that in our swarm will consist of two types of vehicles. So one leader vehicle. Leader vehicle is responsible for global navigation, for leading the whole swarm of vehicles along some predefined trajectory. And we also have a number of followers. We assume that followers are low-cost vehicles, that is, they are equipped with low-cost navigational devices, which means that to cover longer distances that they need leader. They have to follow to track leader. Participants of the project, WTT-71 from Germany and three entities from Poland, so Kraków Polytechnic, PIAP, and Polish Naval Academy leader. We represent with Piotr, with my colleague, Polish Naval Academy. And currently, two other countries are joining the project, so Portugal and Slovenia. Duration 4 years. We started last year. TRL, that is technology readiness level of the final product of the project, is sixth level. Okay, thank you. Before we start our experiments with real vehicles, we decided to start research in simulation conditions. We made some assumptions. You can see 8 points. So first, we decided to use neural networks. In the project, our goal is to develop a swarm control algorithm for follower vehicles. Because leader, as I already said, is responsible for leading. Generally, its task is to go along some predefined trajectory. At this point of the project, we even assume that leader doesn't pay attention to the followers. So, as I said, our goal is to develop control algorithm for follower vehicles, and we assume that to use neural networks as control algorithms. They are supplied, neural networks are supplied, so each follower has its own neural network. Each network is supplied with two types of information, so with information from sensors. How to use it? No. Pointer.
Here, only this.
Okay. So here you can see sensors of our vehicles. Each vehicle has 4 sensors, so 3 cameras located around the vehicle. Cameras are short-range sensors, and we also have sonar. It is acoustic radar, underwater radar, which is no long-range sensor, but let's say medium-range sensor. The range of sonar was approximately, during our research, during simulations, 30 meters. Cameras, the range of cameras, 5 meters. And the other type of information provided to each follower is distance to the leader. Output, heading speed, so each neural network decides, indicates direction of movement and speed of movement. Information or distance messages from the leader, so information about distance to the leader is very rare. Okay, so this information is provided by the leader itself. Leader generates acoustic message to followers, follower by follower. Okay, so if we have 10 followers, and if you assume that the leader generates acoustic message every second, so each follower receives message every 10 seconds. So as I said, information about distance which is received by each vehicle is very rare. No directional information. So vehicles, our followers, don't know where exactly is leader. They only have distance. Homogeneous followers. So followers are the same in terms of control algorithm. So each vehicle has the same neural network, and they are also the same in terms of parameters. So maneuverability, size, weight, and so on and so on. Point 6 is very important. Vehicles can't differ obstacles from vehicles using sonar. Sonar is, as I said, it is medium range sensor, and this sensor is main sensor used by our vehicles. But unfortunately, the problem is that using sonar, vehicles can't differ obstacles and vehicles, so they don't know what to do if something appears in front of them. During our simulations, we had obstacles. We also simulated sea current. There was no requirement regarding formation, okay? Which means that the only task of our followers was to follow leader at some distance, to keep some distance to the leader, nothing else. And currently, I would like to show you 4 movies with results. How to do it? 4 movies with results. Maybe, oh, okay, thank you. This movie is fast. No problem. So we can see the results of our simulation. The first results, okay? Leader is here in the center. In this setting, in this scenario, we used 1 leader and 9 followers. The task of the whole group of followers, 9 followers, was divided into 2 subgroups. One group consisted of 5 vehicles, the other group consisted of 4 vehicles. One group had to keep distance 30 meters to the leader, and the other group had to keep distance, if I remember correctly, 15 or maybe 20 meters to the leader. You can see generally that our vehicles could follow the leader. So neural networks were effective, but what is the problem? The problem is when obstacles appear on the way of our swarm. The other problem is also energy consumption. How we overcome this problem? I will show you some results with obstacles when our followers were responsible not only for following the leader, but also for avoiding collisions with obstacles. Sorry, that is not this. Oh, here. So you can see red circles are obstacles. So initially we achieved some successes, but unfortunately finally we couldn't achieve effective behavior of vehicles, effective neural networks that would be able on the one hand to follow the leader and on the other hand to avoid, here is the situation when leader disappeared from the scene. It doesn't mean that it goes below the obstacle, it goes above the obstacle. It is the problem with application that was used by us to visualize simulation results. Generally, as I said, we couldn't find effective neural networks that would be able on the one hand to follow the leader and on the other hand to avoid obstacles. So we decided to change strategy. And we decided to make a leader as the only vehicle responsible for detecting obstacles and and avoiding obstacles. So the task of the leader is, if obstacle is detected, it informs all other vehicles that in front of the swarm is the obstacle and we have to go up. Okay, so the whole swarm passes obstacles by moving above the obstacles. But for the leader to be able, here is the leader, for the leader to be able to detect obstacles, it can't confuse obstacles with followers. Okay, so no follower can appear here, can move here in front of the leader. Otherwise, it would be considered to be obstacle. So all followers have to stay behind the leader. Okay, and you can see that we achieved such behavior, required behavior of our vehicles. But still, we had problems with obstacles. Why? Because we can assume that our followers are safe, because, as I said, if leader detects obstacle, it says we have to go up. Okay, so all the swarm passes obstacles by moving above the obstacles. So we can assume they are safe. But the problem is that even though followers are safe, they still see not only other followers, but also they see, using sonar, they see also obstacles. So we can consider obstacles as a noise for our followers. Okay. But finally, we achieved neural networks or control algorithms that were able to cope also with obstacles. Here, followers go up, okay, above the obstacles. And that's all. Also. That's all of my presentation, ladies and gentlemen. Thank you very much. Are there any questions?
Thank you for interesting communication. What